The linear algebra solution for linear regression. Well, in a bivariate solution, which is what we looked at when we did the hand regression, the math is a lot simpler. You only have two variables, an independent and a dependent variable. We use linear algebra when we want to solve for a structure of an equation when you have more than one independent variable. So here, for example, we've got two independent variables, IV1 in blue and IV2 in green, and we have a dependent variable which is red. And here we have only four cases, and you can imagine these independent variables measuring something like a score on a test or a quantity of some property, and then it then produces the value out as a dependent variable. So we want to be able to do all the same things we did in the hand regression, which is to come up with a prediction equation and to then insert values for the variables and come up with the optimal ordinary least squares prediction for what the dependent variable value is going to be. And linear algebra is going to help us do this. And so I'm going to take us through one of the solutions, the linear algebra solution for linear regression. So the first step is we need to restructure the equation in what we have here, which is what's called a matrix, which is basically a tableau of numbers. Now, to calculate the sum of least squares calculations, which forms part of the ordinary least squares calculation, we need to insert a y-intercept value. And here we intercept the arbitrary value of 1. Even if it's not the actual value, it's going to be a placeholder and will eventually generate the values that we need in the formula. One of the common techniques used in linear algebra to solve for systems of equations is to do a transposition. And a transposition of a matrix involves rotating each row from the top clockwise 90 degrees and then moving it to the right. So you can see how IV1, which is in blue, is relocated from where it is on the left to where it is on the right in the right side matrix. And you can see the same with the green independent variable, and you can see the same with the y-intercept. So we transpose the independent variables and the y-intercept only, not the dependent variable. The next step is to multiply the transposition that we created in the previous slide against the original matrix. So here you're going to rotate each row from the top clockwise 90 degrees and then multiply. And you can see in the bottom left-hand corner the precise steps of those calculations. So, for example, you would take on the left the series minus 3, 1, minus 7, and 5. You would rotate it, and then you'd multiply it against the matrix in the middle, which lists the four cases, and you'd multiply it against minus 3, 1, minus 7, and 5. And you multiply those, add up those multiplications, and you end up with 84, and that fills the first cell on the top left in the matrix on the right. And then you would repeat that process for the next column and then the next column, and then you move back to the left and pick up the green series of numbers, and then you'd apply the same process and you'd sum up the values, and then eventually you would fill in all 9 of the cells on the matrix on the extreme right. Here are the discrete calculations from the previous multiplication of the matrix against its transposition in case you were not able to see it. You could go ahead and try it yourself. You'll see it's very straightforward. The next step is to multiply the transposition against the dependent variable. Again, you rotate each row from the top clockwise 90 degrees and then you multiply. Here the calculation is much shorter because there's only one column of the dependent variable. And you can see the calculations that are done here in the bottom left corner. And it generates on the extreme right a 3-celled matrix. In case you were not able to see the precise calculations, here they are again. Now here in step 6, we now reunite the two results of our transposed matrix multiplications. You've got IV1, IV2, the y-intercept, and the dependent variable, and they're put back together into a new matrix. Now the core of the solutions in linear algebra is the use of the Gauss-Jordan reduction method. So what we have below are two matrices, one with the numbers that we created before, and a second called an identity matrix. And here you can see a diagonal series of ones from the top left to the bottom right, as well as zeros in all the other locations. Now the essential exercise here is we have to apply 3 arithmetic rules to the matrices at the same time on the left and the right. What we want to do is to convert the matrix that we see on the left until it looks like the matrix that we have on the right. And in the process of making those arithmetic changes, we're going to create new values, and we're going to transform the identity matrix on the right. And those will give us the values we're looking for to solve our linear regression. Now the 3 rules are very simple. The first is you can multiply a row by any number. But of course all the values in that row have to be affected. And of course you're multiplying a row in order to turn it into an identity matrix on the left. The second rule is you can switch any 2 rows. And the third rule is you can add 1 row times a number to another row. So you have 3 very simple rules that you use to convert the matrix on the left into the identity matrix that you have on the right. In the process, you transform the identity matrix on the right. It's like a very complex puzzle. If you don't want to do the puzzle, you can simply go to the link at the bottom, and there is an instant matrix calculator solver. It applies the Gauss-Jordan reduction method immediately and gives you the answer in an instant. But you must be a little bit intrigued by this puzzle. So here we have the results of the Gauss-Jordan reduction method. You can see that we've got our identity matrix. We have a diagonal series of ones, and each of those colors are associated with the variables or the y-intercept that are in the columns. So this gives us then on the extreme right the values, the coefficients that go into our regression equation. So we have a very simple regression equation. It has only 2 independent variables, but the principle applies to no matter how many variables you have. You just end up with very complex matrices. So here the regression equation is y, the predicted value, the dependent variable, is equal to minus 12.4. That's the slope times x, plus 0.42. That's another slope, also called a coefficient, that's multiplied against, in this case, z, which is the second independent variable, plus the y-intercept, where the regression line crosses over the y-axis at 22.42. So this is our regression equation. We can insert values for x and z, and then we can use it as a function to make predictions about the value of y. So this is how we would use linear algebra to solve a regression equation where we have more than one variable. It's a lot easier to do it through linear algebra than to do a hand regression when you've got multiple independent variables in your regression equation. Just so you understand the utility of linear algebra and why we use it to solve linear regressions, another technique is system of equations. One of the solutions of which is substitution. So here we have two equations, 2x plus 3y is equal to 20 on the extreme left, and 3x plus 5y is equal to 10, blue and green equations. And so in this situation, we're going to isolate one of the letters. This is how we do the substitution. So we've got 2x plus 3y is equal to 20, 2x equal to 20 minus 3y. So we alter one of the equations, and we then are able to isolate x from one of the equations. In this case, it's from the green equation, and we can see that x is equal to 10 minus 3 over 2y. We then take that x and we reinsert it. So when you see the red section, substitute x with y, we know what x is equal to. So everywhere there's x, we're going to replace it with 10 minus 3 over 2y, and thereby eliminate x from the equations. And then you can see we can then solve for what y is, because x is gone, and when you've got an equation with only one variable, it's relatively simple to solve what the value of it is, where it's almost impossible to figure out what the value of a variable is if we've got two variables in the same equation. And in this case, y is equal to minus 40. So now that we know the value of of y, which is minus 40, we can then reinsert that into the equation and then isolate x, and then we discover x is equal to 70. And you can see that we verify that in both equations on the bottom left. Another solution is subtraction to solve a system of equations. And again, we have two equations here, green and blue. We're going to multiply the equation, in this case, green and blue, by a value that's going to make them have the same number of x's. Now you can see I put a decimal in front of the minus 3 and minus 6x, the blue equations. That's not an actual decimal notation. It's simply because of the formatting. So imagine that it's not actually there. So here you can see in the subtraction section, we've got 6x minus 6x, which equals 0x. And by this way, we're able to isolate y. And so we see that y is equal to minus 40. We can then substitute y back into the equation. We discover that x is equal to 70. And you can see the verification again on the bottom left. And finally, we have the third solution, which is the matrix solution. I mean, the equations you saw before were very simple. They had two variables, and there were only two equations. But imagine that you had, as in this case, 4 independent variables, not including the y-intercept. And you've got here 7 separate cases. And you can put this into a matrix, and then you could use the Gauss-Jordan reduction method. It's very simple rules to come up with a solution. So this is the power of linear algebra. This is the linear algebra solution if you didn't have a computer to try to solve linear regression. Thankfully, we have computers that'll do it for us in an instant. So be grateful. When I was starting out as a student, we would have to go from one campus to the other and bring our code on a floppy disk and stand up in line at one large computer and insert the disk and then wait several minutes. And then a large pile of brown paper would be printed out and given to us, and we'd have to go through to look at our results. And if there was an error syntactically anywhere, we'd have to start all over again by getting a computer, going back in and retyping all the code. Now you're one key away from your answer.